Who else is going?
Allie, she's
oh, Jeremiah.
He's at a funeral.
And Allie's where?
Doctor, I think.
Okay. All right. So, okay. So number 12. So we got that one out of the way. So what about the book ones? Any problems on those? Those are kind of some basic. Those are like some secant. Was there a tangent or a cotangent?
So when it gives you
Which one?
your advice is just so you just do it with the reciprocal, so if it's cosecant, do sine and then just put the u's in.
Absolutely. Absolutely. So you see secant and you see cosecant, you just put the u's in. That's exactly what you do. Okay, so you graph those first. So what do we have here? 25. So 25 was, am I on the right page here? Okay, so 25 was a cosecant, so you would just do a sine that had a period of 4 pi, right, instead, right? And on 29, 29 was a secant, so you're going to do a cosine, has a period of 2 pi thirds, amplitude 2, right, all that, and then just put the u's on the humps, okay? Where it gets a little trickier is if you get a vertical shift in there, but that's even not that tricky. So on 33, it'd be a sine, and on 35 would be a cosine with the shift. Okay, I definitely want to graph those ones on a couple of those on the worksheet. Talk about those for sure and see how you did there. Okay, because those had some weird markings, and that's what made those more difficult. We're looking at a test on Wednesday, okay, and the test will be over all 6 graphs, so there could be some sine and cosine, so it'll be similar to the quiz that we took. And then, and I got to get, and Claire's still got to take that, so I'm not going to pass that back, but, so all 6 trig graphs, vertical stretches, those kind of things, and then what we're going to learn today. What we're going to start talking about today. Then that'll carry over into Monday too. Okay, it's going to be on the test. All right. So anything besides the graphs on the worksheets, the comment I would make is how I want you to do. Like number 1, it says determine the period, the phase shift, the vertical shift, if any, of each function. Describe any vertical stretching or shrinking. And you also should talk about a flip. Like number 4 is a vertical flip. Number 2 is a vertical flip. You should probably put that in there too. Okay, you can put that under the stretching and the shrinking. Okay. Now, if you left that off on a quiz, I probably wouldn't do that. I think we had one on the last quiz that had a negative in there, and there wasn't a column for that, so that's okay. But so let's talk. So on 2, or number 1, you should say vertical stretch of 2. That's what I'd want you to say. A vertical stretch of 2. Okay, and then a phase shift, pi halves left, and the period would just be normal, be pi. So on 3, you would call that a vertical shrink. 1/5, vertical shrink. At least you're telling me you know that is a shrink. Okay, vertical shrink 1/5. And the phase shift is pi 6 right. It's a normal period of pi, and it's up 5. That kind of thing. Okay, and then you have the same thing on sine or secant, cosecant. Even though we're using sine and cosine, we don't want to call that amplitude. We don't want to call that amplitude. Okay, we want to call that just a vertical stretch, just like tangent, cotangent. So only ones we technically have amplitude is sine and cosine. Okay, so if we did, remember on the quiz there was kind of the boxes and you had to put in there. So I would probably have that first box, instead of just amplitude, I would probably have that amplitude or vertical stretch shrink. So if it's a sine problem, you just put a 2. If that's the amplitude, you just put a 2. Okay, now if you want to say stretch or 2, that's fine. That wouldn't be wrong. That's what it is. Okay, and if it's 1/2, that's the amplitude. You could put shrink, so that wouldn't be wrong. But for the secant, the tangent, those, you should actually then put in stretch or shrink on those for sure. So maybe the safe bet is do stretch or shrink for all of them, even the amplitude. That'd be fine. Okay? All right, so that was really about it for that. Secant function, odd, even, or neither? Even, just like cosine, right? Just like cosine, because you put those u's on there, you're going to have y-axis symmetry, so it's going to be an even function, just like the cosine functions. Okay, all right, so let's pick, let's do the cotangent one. Let's graph number 5 here. Okay, so looking at tangent, cotangent, of course, we have our basic tangent graph that we want to understand where the asymptotes are. Remember, the period for tangent and cotangent is pi. We always want to put that on our fourth mark, okay? For every function that we draw, we want to figure out the period, the amplitude first. We want to put the period on that fourth mark. We want to divide it up. The difference is when we have tangent, we have to put our asymptotes. The asymptote's always right there on the second mark, okay? And then it's every pi unit. So it's a pi halves, negative pi halves. Of course, if the period changes, then that would change that. But that's okay. If the period was pi halves, this mark would be pi halves. This would be pi fourths, and that's where the asymptote would go, on that second mark. It's always, the tangent is always put there. Now, if you're going to shift it, of course, then they'll change. But that's okay, because remember, we do that last. I think the best way to do these, do amplitude and period first, get your marks right, get everything in there, maybe sketch the graph at that point, and then take that graph and move it. Move it up and down. Do the rigid transformations last. I think that's the best plot of attack. Okay, so we get our basic tangent. We know is that. And remember, what are the important points? Some of you have talked about this. This is the part that confuses you on tangent a little bit. Once you got your asymptotes in there, remember, the tangent graph goes up and to the left, and it hits the axis right in the middle. That's the easy one. And then this mark in between, it's always at 1, unless it's been stretched. So then that, if it's been stretched, then that mark might be 2 or 3 or whatever the stretch is, or it might be 1/2 if it's a shrink. Okay, so these marks are the key. All right, those marks are the key. Once you get your 4 marks, once you get your asymptotes in the right place, then you just remember tangent goes that way. Of course, if it's flipped, then it would look like a cotangent. Right? If it's vertically flipped, it would go down and to the right. Okay, same thing with cotangent. Cotangent is period pi. We get our 4th mark marked as pi. We go here. We just have to remember cotangent has its asymptotes opposite where tangent is, right on the axis. Then at the 4th mark, every pi units, right? The asymptotes are every pi units, because the asymptotes repeat just like the function repeats every pi unit. So, and if the period's something different, make your 4th mark whatever the period is, and away you go. And then remember, with cotangent, we go right in the middle, it crosses, and then this one's at 1, and then this one over here is at 1. And then you got it. Now, another thing that might help you is the slope right through here. And this is not a big deal. I'm not going to get that picky on your graphs. But the slope right here is 1, or -1 in this case. So it'd be like at a 45-degree angle. So as it goes through there, so it kind of comes in and it kind of level, it kind of flattens a little, but then it goes through at about a 1. Now, if it's been stretched, it would be steeper than that. Right? It would go through there steeper than a 45-degree angle. And if it's been shrunk, it would go through there a little flatter. Okay? But just to help you kind of draw it, it's not a bad idea to know that. Okay? All right. So anyway, and then of course we have the sine, the cosecant and the secant with the parabola things. Okay. All right. We're not going to do that. So go here. All right, so let's do number 5. Number 5 was y equals, because this was something that a few of you messed up on the quiz. I can tell you that much. Okay, some of you had this backwards right here. What is the phase shift on this graph? Right pi halves. Some of you were getting that backwards, okay? Because you have to take out the 2 before you can get the phase shift. So that is the phase shift. Some of you then, if I gave you one like this, there were a few of you who distributed that through and then called the phase shift pi, okay? We want it in the factored form. That's when we have our phase shift. So this is a pi halves right, okay? So what information is important? My stretch, there isn't one, so that's nice. And the period is the next important thing. And what's it going to be? Period is going to be pi halves. Now that's actually nice. The period's pi halves, and the shift is pi halves. So not only is that a little bit nice, that's a whole lot nice. Because what happens if the period's pi halves and you shift it pi halves? It's like you didn't even shift it. You could literally ignore the shift on this problem. because everything is going to shift over one period, and so we can actually ignore the shift, okay? And so all we have is a basic cotangent at this point, and we got our 4 marks. Here's pi fourths, okay? And since it's cotangent, we know our asymptote's going to go over here and over here, one period. The cotangent goes in the middle there, and here's 1 and -1. So it's going to be at this middle mark, it's going to be at 1, and at this middle mark, it's going to be down at -1, and away you go. And then you just kind of curve it through there. So you can almost make it somewhat straight through here. It's not really straight, it is curving, but you want to curve it in there, come down and do that. And then another period, you could do 4 marks over here and do another period. Okay, actually they said from -pi, did they say? Oh, that was the next section. Okay, that's what made that one a little trickier too. So they didn't really say here, but it would be same kind of thing. So coming down. Okay, so there's your cotangent. So, right, because if you took this and moved it over pi halves would be from -pi fourths to pi fourths. That would be, pi halves is 4 marks. So 1, 2, 3, 4. You move this over 4, it lands right on top of itself. Okay, so maybe it would be good for us to do this other one. So y equals, let's do the tangent one. So we got tangent to, it's already factored, x plus pi halves. Well, I guess this isn't that big a deal either, is it? Because once again, what's the shift? Pi halves, what's the period? Pi halves. Kind of funny, this worksheet's got 2 that are that easy, and then it's got the 2 at the bottom that are way more difficult. So the period is pi halves, so we're going to make our 4 marks. And then we know tangent has its asymptotes here and here, okay? Now, the difference, so we can ignore that shift because it's shifting 1 full period, okay? And then we can, it's just got to go down 1. So if we do this, so now it's down 1. So now instead of my tangent starting right in the middle, got to be down there. And then that point that's halfway over, that's going to be there. And this point that's halfway over, that's going to be down here. And then there it is. And so we come up and we go through like that. Okay? So those 3 points are really the key points you need. The one that would have been here is now shifted down. Okay? All right. Let's move on to those 2 at the bottom, at least one of them. Let's do number 5. Is 5 or 6 tougher? You know that 6 was? Okay, let's do 6. So y equals 4 secant. Now, if you want to do this on another piece of paper, if you feel like you've messed yours up or whatever, feel free to do that. But this one, so the 6 is already factored out. That's good. What is it? Pi what? Halves. And then -2. Now, we're supposed to go from -pi to pi. So that always makes it a little interesting if it's not your normal period for that. Okay? So let's go through here, and we're supposed to go -pi to pi. So I'm going to ignore that here for a minute. So what is my period? What graph are we looking at here? What graph do we want to draw? Cosine, right? So what's my period? 2 pi divided by 6. Don't forget, you got to go back to 2 pi now, right? Secant is 2 pi because that's what cosine is. So it's pi thirds. Okay, so what did we say if you have pi? Well, actually, we don't do common denominator yet. Remember when we haven't had to do this very much, and I don't think it happened on the test, the quiz either. When did we have to worry about getting a common denominator on our marks? Well, our phase shifts is going to be weird already, right? Because pi halves and pi thirds aren't going to have the same marks. But so you might look at that and say, okay, I'm going to need 6 for my divided, but that's actually not true. You have to get your marks on there first before you can do your common denominator. If you remember, I erased and redid my marks after we did the common denominator. So, and to be honest, I forgot that. I mean, I was rushing. I was trying to get it done this morning. I thought, I better draw this out real quick, see what question I have on the answer key. And I forgot it. And I said, oh, I need pi 6. And so I made a bunch of marks, and then I got it done. I'm like, oh, crap, that's not right. Okay? Because here's what's going to happen. All right, so I need 4 marks, pi thirds. So I got a mark right here. Now I got to be careful because I got to go all the way out to pi. So I better, if that's pi thirds, that'd be 2 pi thirds, that'd be 3 pi thirds. So pi will be way out here, right? So this is my 4th mark right here, pi thirds. So now what's that one? Pi 6. And now what's that one? Pi 12s. And here's where you run into trouble is if you would have only marked this as, so this is 1 pi 12, 2 pi 12, this is 3 pi 12s, which would be pi 4s. If you only would have marked that with pi 6, you're going to run into trouble because you're not going to have your 4 marks you need with a period of pi thirds, right? So if the period's pi thirds, you need 4 marks for pi thirds, and so that means you got to actually have it out to pi 12s. Okay, now we look at it, and now we don't really have to worry about common denominator because what's our shift? Pi halves. Well, how many marks? Oh, wait. Well, yeah, we do, because how many marks is pi halves? Where's pi halves on this?
6 marks.
It's actually 6 marks, isn't it? So we're going to have 1, 2, 3, 4. That's going to be 2 pi thirds. Okay, so what was this? 3 pi 12s, 4 pi 12s. This will be 5 pi 12s. This will be 6 pi 12s or pi halves. And this will be 7 pi 12s. And then this is 8 pi 12s. 9 pi 12s would be 3 pi 4s. 10 pi 12s would be 5 pi 6. 11 pi 12s, I mean, it's going forever. And then finally, pi, because we're supposed to go all the way out to from negative pi to pi. Okay? All right, so we're going to actually move over 6 marks, pi halves. Okay? And it's to the left, right? So, and then we're going to go down. And it's a stretch of 4, right? What's the matter, Jack? She's like, oh my God. All right, it's going to go down 2, so we got a stretch of 4. So it's going to go all the way to here, but then it's got to go down 2 more. Right? So we're going to go all the way to there. Okay, so to really have this accurate, it's going to look something like this. Because again, because of this 6, that made our period pi thirds, and that's why we got to have 4 marks for pi thirds. Because now what's my cosine going to be? Well, let's do one before we shift it. Let's do one before we shift it. So a cosine curve normally would be up here at 4. It would be down to here, and 1, 2, 3, 4, and then it'd be down to here, and it would be back up. I'm going to get back here so I can see this.
Do it on the scale of 2.
What's that? Oh, I'm sorry. Yeah, that's fine. This is 1, 2. Okay, so it's a scale of 1. Okay, so this one's up at 4. Thank you. Yeah, this one's up at 4. This one's down here. This one's down here at negative 4. This one's here, and then finally back up to here. Right? That's one cycle of cosine. So there to there. Right? Because remember, because of this 6, I need a period of pi thirds. So that's why I need all those marks. That's one period. So since I have to go all the way to pi, I'm going to have, well, remember we said this 6 is how many cycles you have in 2 pi. So we're going to have 3 cycles over here, and then we would have 3 cycles over here. We're going to have 6 cycles every 2 pi. That's what this 6, that's another way of thinking of that 6. Okay, so then it's going to be back to here, and then it's going to be down to here, and then back to here, and then up to here, and back to here, down to here, back to there, and up. So I'm going to have 3 cycles. It makes sense. If I have 1 cycle for pi thirds, I should have 3 cycles all the way out to pi. Okay, but now, and then I would have another half of this, right? Because if I needed to go this, I just at the time, I'm not going to do all that, but it would you just take all these marks and make it negative, right? It'd be the same thing. All right, now, we got to do what? We got to shift it left. Pi halves, which was how many marks? 6 marks. So I guess I will put them in. I'm not going to label them. 3, 4, 5, 6. So I'm going to go over 6 marks, and I got to go down 2. So I'm going to take this one, go over 6 marks, down 2. This one, go over 6 marks, down 2. This one, over 6 marks, and down 2. This would be down there. Okay, this one, over 6 marks, down 2. Okay, now I'm starting to see where it's at here, so this mark's going to be up to there, so now I don't have to move everyone. Now I know I'm just going to be back to there, and then I'm going to be down to here, right? This one that was a pi halves is going to be over 6 marks, down 2, and then I'm going to be back. So this is like my midline right here now, right? Is down 2. So there's my midline, and so this mark, I'm going to be back to my midline, to my peak, back to midline, down. Okay, how have I done? Have I got enough? Need one more. Okay, this one would be over 6 and down 2 right there. Okay, now, so that is, now remember, that's not even, I'm not even done yet. That's just cosine, right? I still got to do my u's, right? So there's my cosine. Okay, right to there. Now, I would have to keep going, right, because they wanted it negative pi to pi, so I would have a few more, right, to go all the way out here, and I got 6 more of these marks to go up this way. Now, here's the important part of this. Well, obviously, it's all important, because if you haven't gotten this far, there's no way your secant can be right? So now, where do I need the asymptotes? Right here, right? Right here. We said where it crossed the x-axis. Well, this has been shifted down too, so it's like we have a new x-axis. So we've got the black is now the graph we're interested in. So there's an asymptote, there's an asymptote, there's an asymptote, there's an asymptote right there. Okay, so where's it at? It's at pi 4. So if you look at your graph, if you think you got your graph right, you better have an asymptote at pi 4s. You better have one at 5 pi 12ths. Okay, you better have one at pi 12ths. Now think about that. This, what was the period on this? Pi thirds. How many u's are there in a period on the secant? How many u's in a period? There's 2 of them, right? There should be 2 u's. So I'm going to have a u here and a u here. What distance is that? That goes from pi 12ths to 5 pi 12ths, right? I'm going to have 2 u's. Pi 12ths to 5 pi 12ths. What's that? 4 pi 12ths? What is that? Pi thirds, right? So you better, that's where I screwed up the first time I drew this one, is that I looked at it, everything right, but I'd forgotten, I didn't have the right number of marks, so my period wasn't right. So what do we got? We got a U on there, we got a U down here, we got a U down here, a U here, and so forth, so on. Okay, so it looks really messy, right? There'd be a U there. There, all the rest of that, all the red and the blue is just getting it right, so I can put the U's on there. Really, all we care about is the black, as far as this graph.
You gave us this tiny graph.
What's that? Yeah, I know. That's what so that's why I thought it was worth spending some time. Okay? All right. Let's do this. I've kind of, okay, so we talked about test on Wednesday, graphing all 6 of them. Now, again, that one we just did wasn't hard because it was a secant, right? What was hard about it? The shifts and the period, right? So that could have been just as hard on a tangent or just as hard on a sine. It was just because the shifts and the marks, that 6 in there, which made the period weird. That's what made that one hard. So most of the time, it just know the basic 6 graphs. So on Monday, we're going to spend a little more time on that sheet I gave you the other day with the 6 basic graphs. Okay, we're going to spend some time looking at domain, range, and looking at that. So that's something you really want to study. Just make sure you know the 6 basic ones. And then probably most of what you do on the test will be fairly easy shifts and stuff. Probably not something quite like that. Okay, what we want to talk about today is this idea of inverse functions. But I think we're going to wait until, I was going to do that now, but I think we'll wait until after lunch. Well, I don't know. What would you rather do? Would you rather just come back and have fun and do a matching activity after lunch, or do it now?
Do it now.
See, that's just what I do.
I'm ready to learn when I'm full.
Wait, you ready to learn when you're full of food? I like that idea. That's fine, because that's closer, and then the homework is over that stuff, so it might be better to do it after lunch.
Yeah.
Okay, all right. So you need to get in groups of about 3, because I only have 1, 2, 3, 4, 5. I only have 6 of these. Okay, 1, 2, 3, 4, 5. Yeah. So you really probably need groups of 3. Okay. just like we did the other day, match the graph with the,
Stand by yours. Stand by yours.
match the graph with the correct equation. Now you might have to hustle a little bit if you're gonna get them all done. If we don't get them all done, we don't get them all done, but.
Look.
Hallie was trying to get me.
You want to do it over here on the screen? Oh, time for lunch. Oh, I'm sorry to make you strength, dude. Oh, hush with your strength garbage.
Hey, I did lap pull down, did 129 minutes.
Yeah? Do you know what negatives are on bench press?
Nope, don't want to.
You take 30 seconds to let the bar lower down on you. I did that with 205 pounds twice.
I can't even, I benched 205 pounds twice once.
You need to get it up.
No, like, you have someone spotting you because it's literally, like, impossible for you to get it back up.
That's how Andy Mason used to bench. He would go down super slow, and as soon as it hit his chest, he just push out.
Who?
Andy Mason.
Yeah.
But that kid could hang snatch at 85, so.
I saw him deadlift 5 plates once.
No one deadlifted 3 plates and a yellow 2.5, or green and a 2.5.
Alright, give us. Should we just do one at a time? Or?
Sure. This just looks like,
That's cotangent.
it's just cotangent.
This is a
second
one.
Do we need to write these down on a paper?
Yeah, write them down on paper like we did before, just one person in your group, then you can come compare them.
Here, I have.
How many numbers are there?
Should be 15 of them.
Yeah.
Tries to be
1,
like
2, 3.
No, there's just shifted though.
No? No. Because it's signed.
Oh, half, yeah, so it'd be 4 pi 6.
Alright, so
8A.
8 is A, 12 is O, here's Q.
Charlie's G.
That's 6 pi. It'd have to be
1/3.
1/3. 2 is L,
And it goes down to, yep, 15G.
15 is G. So, okay,
This is just.
you're right, no. This is just tangent.
Just tangent.
That was tricky.
The trickiness.
Straight up goobering. 3 sign. I'm looking for a 3 sign.
A letter on it. Oh,
That would
No.
be tangent.
No. Okay, well, this one, look at this. So it goes,
But that's
well, that's a
over.
period of 2 pi.
Yeah.
Oh, okay. I need 1/2 tangent.
You'd need 2 tangent.
Pi over
To
2.
stretch.
So, inverse function. Okay, so we're just gonna do it not with trig functions, but with stuff we already know about. Okay, now you did this last year
What?
or last semester?
Yeah.
Honors algebra.
It was last year.
Well, for some of you, that's true, for everybody. It might have been 2 years ago.
It was 2 years ago.
For some of you, it was 2 years ago. Jeez, they think about that. Wow, it was 2016 since you did that. Okay, now, inverse functions. So, first of all, interchange.
Are you recording?
Yes. So interchange the x and the y. That's the basic idea of an inverse function. Now, when we come back from lunch, we'll talk about why do we need this thing called inverse functions, right? It's going to apply, and it's probably most important with trig functions, okay? But the basic inverse function to look at would be like a parabola, y equals x squared, okay? So to do the inverse, you interchange the x and y. Now, typically what you did in algebra class, I think, is you interchange the x and y, then you solve for y, right? Interchange the x and y, and then solve for y. So what we would do here is we would square root both sides, and that gives you plus or minus square root of x, which is this sideways parabola. Now, the problem, and then of course you look at some points on it like 3, 9, 9, 3, they're reversed, right? They're reversed. And then there's this black line, the y equals x line, that it's like a mirror, right? It's a reflection, and right, you talked about this too, last year, 2 years ago, right? It's a reflection in the y equals x line, because the x and y are interchanged. Okay, so if you draw that in, you can kind of see that mirror reflection. Now the problem is that that red graph is not a what?
Function.
It's not a function. It fails the vertical line test, right? And so the reason it fails the vertical line test, I think we might have talked about this earlier this year, but I know you talked about last year. The reason the red one fails the vertical line test is because the blue one fails the horizontal line test. Does that make sense? If you can draw a horizontal line through a graph, like the blue parabola, when you flip it in the mirror, then all of a sudden that result will fail the vertical line test. So it's fine to the blue one is a function. It passes the vertical line test. The horizontal line test doesn't matter as far as being a function. But if you're going to do its inverse, the horizontal line test does matter. Okay? So a function has to pass both the vertical line test and the horizontal line test if it's going to have an inverse function. Okay? Well, so what we normally do is square root. When we talk about the square root function, what we do is we just do the positive square root. So when we look at the square root function, we just do that. And then we're just talking about the top half of that parabola. And what we do then is by doing that, by making the y's just be positive, that's like saying we're taking the x graph, or the blue graph, and only looking at this half of it. If we only look at this half of the graph of the blue parabola, then it passes the horizontal line test. We can restrict it. Now, why can we do that? Well, we don't need these values here, because these values are just repeats of those values, right? These values over here are just repeats of these values. So we only need this part of that parabola, right? Because when it flips, those repeats end up down here, causing it to fail the vertical line test. So that's what we do to get an inverse function, is we look at a function that fails the horizontal line test, and we just take a piece of it that contains all the values and none of the repeat values. And then we can do the inverse. Well, think about sine. Think of all the repeat values in the sine graph, right? I mean, the sine graph is going to not pass the horizontal line test, right, at all. So we got all those repeat values. So we're going to take just a piece of it to do an inverse. And then we're going to talk after lunch why we need it. Okay, that's good. That got us quite a bit, so we can get through it.
What's the dot? What's the dashed line going in between?
The dashed line is y equals x. That's like the mirror. That's like the mirror, right? That's the mirror image. So all of these points, like this point over here would be a mirror to that point over here, right? This point would be a mirror, right? That's what that line is. Any inverse function is a reflection in that. Okay?
Stop the recording.
Thank you. Back to our notes here. All right, so here's what's important about this, is this idea of restricting, what we call restricting the domain of a function so that it is, actually the term is one-to-one. Remember, did you use that term? Algebra?
No.
One-to-one? Okay, one-to-one means basically it passes the vertical line test and the horizontal line test. If a function passes the vertical line test and the horizontal line test, it's one-to-one. So that means not only is one input give you only one output, but the other way around also. Unlock that too. Would you just flip that? I am. It is that little, just flip that up. There you go. So one-to-one means it passes the vertical line test. Yeah. There you go. So one-to-one means it passes the vertical line test and the horizontal line test. Okay. So we can restrict it to just the green part, and then that passes both. And then when we flip it, right, when we interchange the x and y, it will be a function. It will pass the vertical line test, okay? But it's important that we just can't take any little piece. We want to take a piece of it that gives all the different values. that are in there. And so these values over here are just repeats of those values right there. Okay, so that's going to be an important concept. So here's another one. Don't have to write this one down, but here's y equals x cubed. Interchange the x and y, solve for y, you get cube root of x. The red graph's cube root of x, but the blue graph is 1-to-1, right? The blue graph, x cubed, the graph of x cubed, passes both the vertical and the horizontal line test, so there's no problems. So when we do the flip of it, cube root of x graph is going to be a function, not a problem. Okay, here's e to the x and natural log of x. We're going to talk a lot more about that later in the year, so we won't worry about it right now. But those are inverse functions. So we interchange the x and y. If you remember from Algebra 2, might have done a little of this, but anyway, that when you solve for y, you get y equals ln x. That's the red graph. The e to the x graph is the blue graph. Again, e to the x is 1-to-1. It passes the vertical and the horizontal line test, so no problems with its reflection, no problems with its inverse function. So those are inverse functions. So the question is, why inverses? Why do we even need inverses? What's the deal? Well, it's about solving equations, really. If you think about solving 3x equals 9, that's a nice color. If you try solving 3x equals 9, what do we do to both sides? We divide by 3. Why? Because that's an inverse operation. Now, with add, subtract, multiply, divide, those are operations. And so to solve equations, back in algebra class, you learn about inverse operations. So to solve that, you do the opposite. We always say the opposite. But what you're doing is the inverse operation. So it's multiply, you divide. If it's add, you subtract, so forth. Okay? Well, the same thing is true here, except this isn't an operation that's acting on the x. That's a function. This is the squaring function. This is the e to the x function. This is the sine function. So when we solve these equations, we want to undo the squaring. We have to do the square root to both sides, and that's where we get x equals plus or minus 3. Now, we get two answers when we solve that, and I think I talked to you guys about this being one of my pet peeves earlier in the year, right? What's the square root of 9? What's the square root of 9? Be careful. What's the square root of 9?
No, just positive.
Just positive 3. Because when we talk about what's the square root of 9, we're talking about the restricted, right? We're just talking about the positive, so the square root of 9 is just 3. If we're solving the equation, x squared equals 9, the answer is plus or minus 3, because we're asking, when we solve this, we're asking the question, what values of x work in here? Well, 3 and negative 3 both work. So solving it, it's like when you're doing the unrestricted. But then if you just say square root, that's why when you do the square root of both sides, you have to do the plus or minus square root of both sides, because you want to get both of those answers. Okay? So this idea of restricting and so forth is important. This one, how do we solve this? I'm not going to get into it right now, but what we do is the inverse function of it. The inverse function of e to the x is ln x. And so what we do, one way of solving a problem like this, you don't need to write this down right now, it doesn't matter, but we do the natural log of both sides, because that's the inverse function of e to the x. And what happens? Well, those two cancel each other out, and the answer to this would just be ln 3. How do we do this, right? We don't divide by sign. That's what always drives me nuts when people will say divide by sign. That's not multiplication. We do the inverse sign to both sides, and that's, so far, all we've done with that is you've typed it into your calculator, right? You've done second sine of 1/2. But that's why inverse functions are important. Now, again, this is the unrestricted version. If we were going to actually answer this question, it would be pi 6, it'd be 5 pi 6, it would be ... There would be a ton of answers, right? Think of the unit circle. Pi 6, sine is 1/2. Over here at 5 pi 6, sine is 1/2. Come back around. 13 pi 6. You could just go around all day. And you could go backwards to negatives, right? There's an infinite number of answers here. However, if we do the arc sine, and that's a term you're going to learn here in a few minutes, but that's basically inverse sine. Another way of writing it is this. They're both the same. There's two ways to do it. One is arc sine, one is this. I don't like this notation because it makes it think reciprocal, and it's not. It's inverse sine. On your calculator, it's when you hit second sine. But this is saying we do the arc sine or the inverse sine of 1/2. Well, if you type that into your calculator, you're going to get 30 degrees. If you type into your calculator second sine 1/2, you're going to get a 30 if you're in degree mode. Okay? Because that's what it is. Notice it only gives you one answer. It didn't give you all of this, because your calculator is programmed with the restricted inverse sine. The one that is a function, that you put one thing in, you only get one thing out. Okay? So again, difference between solving and inverse. But that just gives you a sense of why we need this concept of inverse functions. Because when we're trying to solve these equations, we have to do the inverse of it to get the x. Okay, so now let's talk about the inverse trig function. So let's go ahead and start over here on the left. Start over here on the left if you're wanting to write this down. Okay, so the inverse trig. So let's talk more about this inverse sign. When you look on your calculator, it's above the sign. It says sine -1. Now, to be honest, I'd rather call it arc sine, which is just another name for it. I just think that's less confusing than sine -1, because that looks like reciprocal, even though it's not. Okay? So what do? We have a normal trig function here in blue. So let me explain this as you write it down. Y equals sine x. Now always remember, and this is where this becomes important, always remember that into a sine function we always put an angle. Degrees or radians, one or the other. So inside of a sine function always goes pi 6 or 30 degrees or something like that. We do the sine of an angle. And we get out a value. Now we've learned with our sine graphs that the value we get out is always between what and what? The value we get out of a sine function is always between what and what? No? -1 and what? Right? Think of the sine graph. The y values on the sine graph are what we're talking about. The values we get out of a sine function are always between -1 and 1. Now what can we put into the sine function? Anything, all reals, right? So angles go into a sine function like pi 6 or pi thirds or whatever, 30 degrees, 45 degrees. We get out a value. We're always going to get out a decimal between -1 and 1, like square root of 2 over 2 or root of 3 over 2 or 1/2, right? Okay. Always understand that. So the x and y. X is an angle, y is a value. So now let's interchange the x and the y. So now let's put the x over there in the value spot, and let's put the y in there in the angle spot. I put that in red because now that's our inverse. Right? Once we interchange the x and the y, that is now our inverse. Right? Remember from Algebra 2 class, how do you get an inverse? You start by interchanging the x and the y. But the y is now the angle, and the x is now the value. Okay, now we want to solve for y. Well, how do we solve for y? How do we get rid of the sign? We undo it by doing inverse sign. So we come over here, and so we now get the y by itself by doing inverse sign to both sides. And then I flipped it. I flipped it around so the y was on the left. Okay, so we do inverse sign, so the y is now by itself, and over here we have inverse sign of x. And then I just flipped it so the y comes first. Okay? Now remember, x was the value, the -1 to 1 thing, and the y is the angle. So over here, y is the angle, x is the value. So what's going to go into an inverse sign? It's going to be the -1 to 1. Now, it should make sense. In the regular sine graph, the -1 to 1 is the output. It's what we get out. If we're going to interchange x and y on the inverse, it should be what we put in. Make sense? The inverse sign, what goes in is the -1 to 1. What you get out is the angle. Okay? So we write it one of two ways, either sine -1 or arc sine. Okay? Now, there's a couple ways you can read this. I don't know what makes more sense to you. To be honest, this one I don't like as much. When I see arc sine, I'm going to think the angle. I kind of went back and forth how I wanted to talk about this. I'm going back with what I originally liked. When you see arc sine or inverse sine, I think this is what you ought to say to yourself. It's the angle whose sine is x. So if we were doing arc sine of 1/2, we would be thinking to ourselves, the answer to that is the angle whose sine is 1/2. Arc sine 1/2 is the angle whose sine is 1/2. Okay, which of course is pi 6, but it also could be 5 pi 6, it could be all these other things. Well, you know, in a function, you don't want to have a bunch of answers. When you put in a 1/2, you want to get out one answer. Okay, and so that's why this whole part of restricting and all that 1-to-1 and horizontal line test comes into play. Okay, so what does this look like as a graph? So let's go, I'm going to go to Desmos instead. Well, I'll just show you this. You don't have to write this down just yet. Okay, look at that. Okay, it gets pretty messy. But look at the blue. It's kind of pretty. But look at the blue. The blue is your normal sine curve. Then you got the y equals x line in there. Doesn't it look like the red is the mirror image? Looks like it's a reflection, right? Now clearly it fails the vertical line test. Why? Because the blue fails the horizontal line test, right? But let's just take a couple points. For example, here you got pi halves 1. So what point should be on the red graph? 1 pi halves. Well, where's 1? Right here? 1 pi halves right there. So I just put them on here. Here's 1, 2, pi halves about 1.57, right? So I just stuck it right about where it goes. Okay? So 1 pi halves. Here's a point pi 0. So the red graph should have 0 pi. There it is right there. So all of these points that repeat on this graph repeat on this graph, right? And of course, we don't want that, right? We want to restrict it. Okay, so what are we going to do to restrict it? So let's go to Desmos, and let's take a look at this. Okay, so there you see my parabola. Notice I got my blue parabola, which is not a function. Now look what I did over here. I got y equals x squared, and then I just wrote x equals y squared. I just interchanged the x and y. So the graph goes ahead and graphs it, not like a function, but all the points. Okay, now let me turn that off, and let me restrict y equals x squared to just that part of it. So it's now 1 to 1. It now passes the horizontal line test. Now what's its inverse? There's its inverse, right? That's just the top half. That's the square root function. Okay, let's do that with sine then. Okay, so here's your normal sine graph. All right, and so what if I do interchange the x and y, x equals sine y, look what I got. I got the thing I had drawn by hand. Okay, but now let's restrict it. Now where should we restrict, you suppose, the sine graph? What piece should we grab so it passes the horizontal line test, but includes all the values? Now there'd be multiple pieces you could pick. So where? Here to there? Wouldn't that be a piece that would work? That gives me all the values from -1 to 1, and it doesn't give me any repeat values, because once I go past there, now I could take this piece, right? So we're going to take the piece from negative pi halves to pi halves. Now which quadrants is that in the unit circle? Negative pi halves to pi halves. Where's Nate? No? 4. Unit circle. Oh, I see what you're doing. Yeah. Here. Here's negative pi halves right here. Right? And here's pi halves. Okay? So you're saying if you go around and go negative pi halves to pi halves, that'd be that way. But remember, this is negative pi halves. If you go that way, that's going to be negative pi halves to negative 3 pi halves. So that's going to be 2 and 3. Negative pi halves to pi halves is this and this. Because that, yeah, it'd be going this way. Now you're right, you're saying, well, that's not negative pi halves. Well, it is. If you go down to here, call that negative pi halves, you go up to here. So it's 1 and 4. It's 1 and 4. Now, why 1 and 4? Well, because what is sine up here? Positive. What's sine down here? So that gives us both values. Okay, so do a little test on your calculator. Okay, do a little test on your calculator. So let's do second sine of 1/2. Do second sine of 1/2. Be in degree mode, probably. Second sine of 1/2. Should get 30 degrees, right? Now do second sine of negative 1/2. What do you get? Negative 30. Negative 30. See, you don't get 330, right? That's why you get negative 30. And I talked about it when we were doing the calculator the other day, but we weren't getting into this yet, so I didn't want to make a big deal about it. That's why negative pi halves and pi halves is like saying we're going here and we're going here. It's kind of like split. So we're going here and here. Here will give us our positive values, here will give us our negative. So that's why if you put a negative into the inverse sine function, you get a negative out, because we're doing those two quadrants. So we're going up to pi halves, we're going down to negative pi halves. So you get 30 or you get negative 30. Okay? Now, let's take a look. So you're exactly right. We don't want the whole thing. So we want to restrict sine to just that piece right there. So everybody looking up here, you see it? We're just going to restrict sine to that piece. So the arc sine, so if I ask it to do the arc sine function, it's just going to give me that little piece right there. Okay? So it's a function. So when I do this, it gives me the whole thing. X equals sine y, but that's not a function. Right? Here I write it as the arc sine function, and we want to restrict it. So that's what the calculator is giving us. And so those are the pieces we're getting out. So understand why the calculator gives you that. Now, if I ask you to arc sine 1/2 and I tell you I want the answer to be between 0 and 360, then you would take that negative 30 as a reference angle and then you go around and you say 330, right? So that would be its name, coterminal, all right? So understand those quadrants. Okay, so what about the other trig function? So just what you've already learned about inverse, but when we go to our calculator, because that's mostly what this is about, when we go to our calculator or we're having to do a problem without a calculator, we understand it's still mostly about the unit circle, and just understand why the calculator is giving you what it's giving you, and why it's only giving you one value out, when we know there'd be a whole bunch of different values that get sine, where sine is 1/2, right? So what about cosine? So here would be cosine, okay? Obviously the red is not a function, okay? So let's go back to Desmos. Where do you suppose we could restrict it? Where do you suppose we could restrict cosine so we would only get one piece? One little piece. From 0 to, I think 0 to pi would be a good one. Now you could say, well, you could go from here to here, but why go negative if you don't have to? I think 0 to pi is a good one. Now what quadrant's that? That's 1 and 2. 0 to pi is 1 and 2. Now that makes sense because cosine's positive there and negative there. So now let's do a little experiment again. So let's do second cosine of 1/2. Let's do second cosine of 1/2. Better get 60 degrees, right? Better get 60 degrees. Now do second cosine of negative 1/2. Do second cosine of negative 1/2. Now you might be expecting negative 60. But you don't. What do you get? What do you? 120. Why? Because what quadrant are we in? Second quadrant. The calculator knows. I mean, the arc cosine, the inverse cosine function in your calculator is programmed with that restriction. So inverse cosine is going to stick to quadrants 1 and 2, okay, between 0 and pi. So you're always going to get an answer between 0 and 1/8. So it gave you 60 for positive 1/2. It gave you 120 for negative 1/2. Okay, it's in that quadrant. All right, and I don't have it set up to do the restriction on this one, but I can show you just arc cosine, and there it is, 0 to pi. See, going up is just 0 to pi. So it's going to give you answers from 0 to pi. Okay, and then finally, tangent and arctangent. Okay, so here's arctangent. Okay, or excuse me, there's regular tangent. So arctangent's kind of crazy. The inverses, they all go that way, right? Let's put the y equals x in there, but they're all kind of flipped. But it's a little busy. There's a lot of stuff going on there. So what could we restrict just the tangent curve to get all the values? So it passes a horizontal line test. What piece could we look at so it passes a horizontal line test? Just one branch. Just grab this branch right here, right in the middle. Just grab one branch and ignore the rest, because one branch is going to hit all those values from negative infinity to infinity. So what is that? It's from negative pi halves to same as sine. So sine and tangent are the same restriction. So what we're going to do is, I don't have it set up again to do that, but if I do arctangent, there's arctangent. It just takes this one branch and it does the inverse. Kind of like x cubed. It looks a lot like x cubed actually. Okay? But there's our one branch, and then that passes the vertical line test. So let's test it. So let's do inverse. Let's do an easy one. Let's do inverse tangent of 1 on your calculator. Do inverse tangent of 1. Okay. What do you get? 45 degrees. Let's do inverse tangent of negative 1. What should you get? Think about it. Should get negative 45, shouldn't you? Because you're getting first quadrant, fourth quadrant. Remember, tangent's positive in the first quadrant, negative in the fourth quadrant. So that'll give us all the values that we need, but it's going to be negative pi halves and pi halves. Okay, so that's why it gives us what it gives. So cosine's kind of the weird one. Cosine just goes 0 to pi. That's quadrants 1 and 2. Okay, so when we go to second sine, second cosine, second tangent on our calculator, that's why it's giving us the values it's giving us. Okay, because it can only give one, right? All right, so that is a quick look at that mess. That's why I went to Desmos. As bad as Desmos, I started drawing that like, oh my gosh, that's awful. Okay, so
It's a pretty firework.
it's good, yeah. All right, so, all right, here's what your homework question would be like this. So the idea is, all right, sine theta equals 1/2. Now again, if you were actually solving that, if I didn't tell you anything else, we're going to get into this next week. That'd be pi 6, that'd be 5 pi 6, that'd be 13 pi 6. It would be, on and on and on. It'd be negatives. It'd be all over the place. Okay, you could get negative versions, all the coterminals. So there'd be an infinite number of answers. But what we do to solve it is we say, okay, let's do the arc sine. Let's do the inverse sine. Where's the sine equal 1/2? What answer? If we're solving an equation, then yes, we want to consider all those things. Just like if we're solving x squared equals 9, you got to think about plus or minus 3. But if I ask you what's the square root of 9, I'm only asking for that one answer. It's a function. I'm asking for one output. So if I ask you this, right, I'm just going to get one answer. Now again, I don't like that. I'm going to say the angle whose cosine is -1. That's what I'm going to be saying here. Okay? Now, if you like what I'm crossing out here and you want to do that, I don't care. But you're going to hear me saying this. The angle whose sine is 1/2. Now, if you're given the problem this way, as a function, as the arc sine function or the arc cosine function, there's just one answer. So what you got to know is which one is my given? Where's my restriction? Okay, so arc sine, what did we just do? We just did this one in our calculator, actually, didn't we? What is theta on this one? Well, what'd you get? Remember, arc sine 1/2? Where is sine 1/2? 30 degrees. Now, if we're in radians, we would write pi 6, right? If we're in degrees, we would write 30 degrees. Okay? What angle has cosine of -1? Think of the unit circle. Cosine is the x. That's over there at pi. Now, you could do negative pi, but wait a minute. What's the restriction for our cosine? From 0 to... Our cosine was the one that was 0 to pi. The others were negative pi halves to pi halves. Okay, so the cosine restriction is 0 to pi. So the answer to that one would be pi. And I'll bet if you tried on your calculator right now, if you tried second cosine -1, I bet you get 180, right? 180 degrees. If you do second cosine -1, you get 180 degrees. Okay, that's pi. All right, so here's what your homework's going to look like. When you see these decimal ones, that means calculate. When you see the other ones, it means do it without a calculator. The test, there will probably be a no calculator part to the test. Okay, so let's go through them. Let's see if we can do it. Now, I don't care if you grab your unit circle right now, for a little while to do it. Just remind yourself, but this is saying the angle whose sine is -1/2. So what quadrant where sine be -1/2? 3 and 4. Sine's a y. But we don't want both 3 and 4. We only want one answer. Which one do we want? We want 4, right? Because arc sine is negative pi halves to pi halves, as we just talked about. So arc sine's in 3 or is in 4. Okay, so what's it going to be? It's a 30-degree reference. It's going to be -30 degrees. Or negative pi 6, because isn't that the one we just said? Well, you're not going to get 330, right? Because that was the one your calculator gave you -30 degrees, right? Positive, it gave you positive 30, it gave you negative. Remember, this is from negative pi halves to pi halves is our restriction. So we're going to get an answer that's negative right there. So yes, you're thinking reference angles, you're thinking all that stuff we've learned before. Okay? And this is the same thing as arc sine. This is saying what angle has a sine of √3/2? So just go ahead and take reference right away. 60, right? 60. Now, that's a positive √3/2, so what quadrant we want? We want quadrant 1, so 60 is going to be our answer, right? So depending on the question, you're either going to put 60 or you're going to put pi thirds. Okay, this is all your homework's going to be. Okay, there's going to be a handful of them that are this, and then there's going to be another number that are used. Type in your calculator is all you do. Okay, should be cosine √2/2. What angle has a cosine that's √2/2? 45. Now cosine is 0 to pi, or cosine 0 to pi, that's quadrants 1 or 2. Which one do we want? We want 1. So positive ones are nice. They're always in quadrant 1, aren't they? So it's the negative ones we got to think about. So 45 degrees or pi 4s. Okay? Arc tan, -1. tan, -1. Oh, wait a minute, tan's y over x. When do the y and the x the same? 45 degrees. But we want negatives. Which quadrant? Remember, tangent's just like sine. It's either 1 or 4. You're right, tangent's negative at 2 or 4, but which one do we want? 4, right? Because we're going to do 1 for positives, we're going to do 4 for negatives, just like arc sine. 1 for positives, 4 for negatives. Even though 2 would be another one, but we don't want it, right? This is a function, we only want one answer, so what do we put? -45 or -pi4. Okay, that's what your calculator would give you if you try it. Okay, that's what it would give you. Okay, and you see one like this, you just type it in. Just type it in. Okay, you just type it in. If you want to be in degree mode, that's fine. You want to be in degree mode, depends on the directions. If they want both, if they want degrees and radians, you could put it in degree mode, then change your calculator to radian, and then do second sign again, and that'll give you the radian test. Okay, so you get one of those, you just put it in. Now, put in that last one. Put in arc cosine 2.31. What do you get? You get an error. Oh wait, why would you get an error? Say it again. It's bigger than 1. Remember, what we're putting in are the values. We're getting out angles. And we already know that cosine and sine values are stuck between -1 and 1. So there's no angle whose cosine has a value of 2.31. Never. So you get domain, right? So one like that, we should just know right away. So be careful one like that on the no calculator, right? If you had one like that on the no calculator, arc cosine of 2, say, no solution. No solution. Okay? Sorry to go so hard on you on a Friday, but not really. You guys are good. You can handle it. But the homework's easy. Okay? The homework, now, I say easy, there's not a lot of it. Okay? So 5 through 20 are no calculator. So those are going to be things like root 3 over 2. That's where you really practice your understanding of this. Okay, now if you want to check on the calculator, okay, I get it. But understand, on the quiz, you're going to have to do 5 through 20, no calculator on the test. So that's where you really get this idea of what quadrants are we stuck in here. Okay, now, 23 through 39, just type in your calculator and go. Okay, just type in your calculator. If you run into one, well, let me see here. I don't think you will. All right. Good job.
I excel. You get all this stuff thrown. You don't need to do this and this and this. I don't have time. Bless you, Seth. That's bad. I've been out of this course like, yeah, I would go. Okay. My friend is the guy who was in the phone. So he held it in. It literally happened. If they have the training for it.
I was expecting like, you got stickers.
Don't clean it. I was like, don't clean it. What was that?
What? What happened?
When you were recording.
Well,